This computer. Okay. So welcome you all to take part in the 8th gauge gravity by the Ghat seminar. Today our speaker is Aaron Held from ENS. He is currently a distinguished postdoc at Lapins ENS. So prior to joining ENS, he was a postdoc at Princeton, Jena University, and Imperial College. He has done his PhD from Heidelberg University. Aaron works largely in the area of classical and quantum aspects of gravity, which actually covers quite a big thing. And uh, and today he will talk to us about stability in the presence of higher derivatives from point particles to gravity. So Aaron, welcome to the gauge gravity seminars.
Yeah, thanks a lot, Gaurav, for the invitation, and thanks a lot for the kind introduction. Indeed, I come from quantum gravity, and I started exploring classical, and in particular strong classical gravity in recent years, more and more. And so today I won't talk much about any of the quantum aspects of my work. I really want to narrow in on this focus of stability in the presence of higher derivative terms. And so let me also say that whenever you have questions, feel free to ask them right away, because I think I might be too short on something or so, and if that prohibits understanding, that would be a pity. So whenever there's anything, feel free to interrupt me, then we can have a nice conversation. Also, let me say that the talk will have 3 parts. I will start on basically, I will start with a motivation, which will contain a little bit of why I'm interested in these higher derivative terms. And then I will turn to toy models in some sense, to point particle systems, and ask the question in how far we can make sense of these point particle systems. And there, of course, the big question is the Ostrogradski instability, and if we want to make sense of this, we need to somehow find a way to deal with the Ostrogradski instability. And I will give you an example of how this might be possible, at least for point particles. And then I will change gear a bit and return to the gravitational effective action and talk both about local stability or linear dynamics, and then about nonlinear stability and full nonlinear dynamics. Finally, before I get started, let me say that these different notions of stability really are very different things, and they don't necessarily imply each other, and there can be counterexamples to each of these. So it's very important to tell apart global stability, with which I will simply mean that whatever initial conditions you put, your motion remains in a finite phase space volume. Then local stability, by which I really mean that if you have a local trajectory, it's stable against small perturbations. So if you perturb it a bit, the trajectory remains close by. That's the notion of stability that you're presumably most familiar with. And then nonlinear stability, which is just a technical term in some sense about nonlinear evolution of partial differential equations. All right, so with all that preface, let me get started. So I want to start with the effective action. And that's sort of my motivation for why I think it's interesting to revisit higher derivative terms and to try to make sense of them. And that's of course just because any form of quantum correction will induce additional fluctuations and therefore additional terms to a classical action. So how would we go about expanding such an effective action, right? We want to write down a tower of terms or even full functions of terms in, for instance, curvature and momentum. And so what I'm going to show you here on these very first slides is in some sense an expansion in curvature and an expansion in powers of momenta. And in gravity, there's a relation between the two because the Riemann tensor carries not only curvature, I'll give it an index 1 for curvature, but it also carries 2 powers of momenta. While then there can be derivative operators, and I've shown you here the box operator, which has no power in curvature, and 2 powers in momentum. And then you can slightly reshuffle that to make it symmetric in ones and zeros. So you're basically defining a new counting variable. And then you can start expanding actions. You can identify the two, but you don't need to. And so general relativity would be np tilde 0 and nr equals 1, which would just mean that it has 1 power of curvature at most and no external derivative operators. And you can go on and you can go to power 2 in curvature, where you then pick up terms which are proportional to the Ricci scalar squared and to the Wild tensor squared, where squared I mean a particular index contraction among the Wild tensor. Of course, you can write down some additional terms, but they're all equivalent upon identities. And so this is the most generic thing in some sense, apart from boundary terms, that you can write down at the quadratic level. And then you can in principle go on. I will later on be interested in this particular action because it's in some sense the simplest one that shows you this higher derivative problem in gravity. But you can go on and you can go to cubic gravity, and then there are terms like those here where you contract multiple terms, multiple Riemann tensors into each other. You can, of course, again, write down a bunch of others, and here I've only written down terms which are, first of all, using all the identities they have in 4 dimensions, and also, second of all, removing terms which are equivalent upon field redefinitions and use of the equations of motion of the lower order. So in that case, you can think of any Ricci tensor vanishing because I'm using the vacuum equations of the lower order. Whether you want to do that or not is the question in itself. And then you can go on and go to quartic interactions, where this again are symmetric contractions of the Riemann tensor squared and a dual Riemann tensor squared and a mixture of the two, and so on. And of course, this takes you higher in this curvature counting here, and it doesn't increase this np tilde. And what is interesting is that all these theories remain 4th order in the equations of motion. So indeed, they remain propagating the same number of degrees of freedom. Of course, how the degrees of freedom are entangled, where entangled I just mean mixed and not entangled in any information theoretic sense. How these degrees of freedom mix depends, of course, on the particular order and the particular nonlinearity, but it's just these degrees of freedom that propagate. And indeed, that's true even if you write down a theory of an arbitrary function of the Riemann tensor, just because you're not adding external derivatives. And there's a linear proof of that, and I'm working on a nonlinear proof of that. So in any case, that's sort of following the tower of going to higher curvature. So that indeed saturates to these degrees of freedom, where I will be very specific towards the end of my talk that these 2 degrees of freedom correspond to the usual.
Aaron, I just wanted
Yes?
to ask just one clarification. When you are adding these higher derivative terms, you are just within the requirement that you are respecting diffeomorphism invariance largely all the time.
That's right.
Yeah,
That's
I
right.
see.
Not just largely, I'm respecting diffeomorphism invariance.
So if
That's
you
right.
break, like there will be more terms will be in the series.
For sure. If you do
Yeah.
that, then you will get additional terms. Yes, that's right.
Okay.
And I will not do that at any point during the talk. Thanks for the clarification. All right. Then, as I said, that saturates sort of the degrees of freedom in this going to higher curvature. This is the metric. Yes, yes. Okay, so this is the metric. This is a scalar degree of freedom, a massive scalar actually, and this is a massive spin 2 degree of freedom. Therefore, it has 5, it encapsulates 5 degrees of freedom. And this one here will come with the opposite sign kinetic term than this one here, which is the usual ghost problem. that you might be familiar with and that I will talk about in the coming bits of the talk. Notice that if I would increase the derivative powers, then I would basically add box operators, or at least covariant derivatives. In gravity, it's a little tricky because you can contract them into the Ricci tensor itself. Then we don't know which degrees of freedom that saturates. Presumably, it doesn't really saturate. At each order, you have more and more degrees of freedom, and you can only really make sense of this in a way of finite degrees of freedom if you go to infinite order again and remove these fiducial degrees of freedom. What I want to say with all of this is that I'm very sure that these degrees of freedom here, or it seems reasonable that these degrees of freedom are indeed fiducial due to the fact that I truncate the series. Which degrees of freedom of these ones here I should take as the fundamental degrees of freedom of a diffeomorphism invariant action is less clear to me and becoming less clear to me as I go on. Of course, the only degree of freedom that we observe is this one here. So for sure, this is the most relevant one. And you could also discard those two here as fiducial. Yeah, go ahead.
Yeah,
yes,
so
sure.
I'm trying to understand this this choice of degrees of freedom and in some slightly more general terms. I'm not sure I fully understand the quandary that you have. If you don't mind, if you could just spend a few more minutes explaining that.
Sure, but can you be more precise about what you don't understand with that concept?
I mean, the fact that you've got these 2 degrees of freedom coming from, of course, from gravity, which you're confident of, but the other is that. I mean, you just made a statement, and I'm trying to understand why, from whatever you've said, that's the system you're dealing with. So why is there? I mean, I don't see an ambiguity. Maybe that's what I'm missing, some subtlety. So if you could.
So I think the way that I think about degrees of freedom is I think about it in 2 ways. One is really just linearizing the action. So if I would go back to this action, which I will look in a lot in the later 2 parts of my talk. So you might want to derive the equations of motion and linearize the problem, and then you can really look at what linear modes do I have in my equations of motion, and then the answer will be these ones here. And then one step further, at least in my understanding, is if you go to the nonlinear problem, and you will see that explicitly in the end of my talk, then you can also identify initial conditions which correspond to these degrees of freedom. So in that sense, even in the nonlinear theory, I think there's the same number of initial conditions, and in that sense, the same number of degrees of freedom. And that's at this point all what I mean with degrees of freedom.
I think that's clear. Thank you. Yeah.
Okay. And then just to add, then it makes a lot of sense that these saturate if I don't increase the number of derivatives, because then it means that my equations of motion don't increase in order, and therefore I only need to set a finite amount and the same amount of initial data. All right. Thanks again for the question. Let's keep this up. Please do ask lots of questions. Just let me add that if I were to now write down full functions of derivative operators, such as this one here, imagine there would be a function, and this is what people in the community that I come from call form factors, but you might also be familiar with this in terms of non-local gravity, where you really have a full function here of the box operator, and then the propagating degrees of freedom depend on the poles in that function. And you might just have the usual propagating degrees of freedom or additional ones if you have additional poles in essentially the propagator, and therefore in this f of box function. The same holds for the other degrees of freedom that I had before. So there might be additional degrees of freedom due to poles in the propagator. And these functional forms and also non-local terms are in principle also induced by quantum fluctuations towards the infrared. So in some sense, we might even have to deal with such non-local corrections. So this is sort of a broad picture of what I think quantum theories do and what difficulties this poses even for the classical interpretation of the effective action. All right. So as I said, most of the time in the later parts of my talk, I will focus on the simplest among all of these additional actions that you can write down, and this is this quadratic gravity action. And of course, now you may raise the question, why am I not ruling out these extra degrees of freedom here as being non-fundamental? Because indeed there is an Ostrogradski theorem, and so I should maybe consider that any theory which propagates these degrees of freedom is unstable. And indeed, that is the generic thing that happens, but it's not a one-to-one correspondence, and that's what I want to spend a bit of time about in the first part of my talk. So the usual statement goes that all higher derivatives theories are unstable due to this Ostrogradski theorem. I want to be a bit more careful about the statement of the theorem. So first of all, it's of course a statement about non-degenerate higher derivative theories. So you need to be able to write down a full Hamiltonian in which you disentangle these modes. It's also strictly just a statement about classical point particles. So Ostrogradski's original paper from way back is just a construction of higher derivative Hamiltonians for point particle systems. And then it's a statement about whether these point particle systems, or people often say that it's a statement about whether these point particle systems exhibit so-called runaway solutions. So solutions which run away to infinity faster and faster over time. And also that is not quite true. So it's actually a statement about the Hamiltonian itself of these higher derivative theories. And it's simply the statement that the Hamiltonian, if you define the Hamiltonian as Ostrogradski does, of all higher derivative theories of classical point particles is unbounded both from above and below. And the rest is physical extrapolation, as far as I know. So taking an unbounded from above and below Hamiltonian, the typical conclusion is then that that must exhibit runaways. And that's exactly what I think is not quite correct, because there are counterexamples to that. The first one, really where it's proven to my knowledge, is this one here, which made me become very interested in this topic and collaborate with these people. And I think we have somewhat an understanding of both the exact way of proving this in certain systems and about the physical implications of this by now. And that's what I want to talk about in the first part. All right, so my statement is that even though that's correct, that Ostrogradski theorem implies that a Hamiltonian is necessarily unbounded from above and below, it's exactly this unboundedness from both sides, given the kinetic terms having opposite sign, which makes these theories nevertheless potentially globally stable. And when I say globally, I mean again Lagrange stable in a sense of all initial conditions remain in a finite phase space volume. All right, so let me get started with this, and that's a summary in some sense of recent work with Cédric Defayet, Shinji Mukuyama, and Alexander Wickman, which is published in JCAP as part of the 20th anniversary edition. All right, so this is the way that the problem is tackled in this paper is by means of integrable systems. And the reason is simply because the additional constant of motion that you have, or potentially many additional constants of motion, allow you to have another quantity, such as the Hamiltonian, with which you can bound momenta and position variables. So that helps you in just technically performing a proof of stability or of global stability. So the systems that I want to look at are really now just point particle systems. So in basically the simplest systems that you can think of two modes. So one momentum for one mode X and one momentum for Y, with some sigma here, which just indicates whether I am in the Ostrogradski case or not. So whether I have a wrong sign kinetic term or not, whether I have a ghost or not, and some potential which couples the modes, but just in terms of X and Y. So I'm not considering potentials which include momenta for the moment. And then people have asked, and for instance, there's a nice review by Heta, which I don't have on the slides here, but I can point you to if you're interested, have constructed systematically among this class of theories which have additional constants of motion, and one of them is this particular one here. And that's the only reason why we consider this particular construction of the potential, where you see there's two full functions still of the position variables, and then a particular combination of the position variables, where u and v are again particular combinations of x and y in this particular form. Again, the form is necessary such that the system remains integrable. During the course of this work, we can understand now that there are stability conditions on these functions, and effectively these stability conditions, you just need them in the proof as parts of steps to bound the respective quantities. So you can think of the first condition as being necessary such that the additional constant of motion bounds particular combinations of the momenta, and then the second condition to be necessary to bound particular combinations of x and y, so that in the end you can conclude that all the phase space variables remain in a finite part of phase space volume. I think it's not particularly illuminating to go through the proof, and therefore I just refer you to the original paper if you're interested. And of course, feel free to ask me more details about it. What I want to add is that these particular models contain polynomial subclasses. So you can pick particular combinations of these functions f of u and g of v, and you can prove then that the potential becomes polynomial. So that happens, for instance, if you pick these particular form of the functions where these coefficients here need to be the same in both functions. And then there are polynomials such as this one here. This is in some sense the lowest non-trivial order, which can be stable. It exhibits now some frequencies or some mass terms, and some particular interaction structures which depend on these mass terms and on further couplings in your tower. But it's a polynomial action, and so in some sense we do now also have polynomial examples of such models which are stable. All right, so now let's take such a polynomial subclass, and the sort of graphical way of convincing you about stability is just to plot the trajectory. And now you can really see that if I look at the phase space volume, and you can of course make a similar plot for px and py and think of this in a four-dimensional way. What I'm showing here is the trajectory colored from black to white, going over green in time. And I'm of course only showing a snapshot of the evolution. So this is exactly not a proof. It's just a numerical sort of visualization of the proof. But what you can see here is that the initial condition stays in a finite phase space volume. And indeed, I encourage you, it's not super hard to implement these types of point particle evolution and just play around with it. I found it very convincing to see that if you just throw random initial conditions, indeed you always remain in a finite phase space volume. Yeah, so that's, and this is the px, py version of the plot. Let me just add that the numerics suggest that integrability was necessary for the proof to find this boundedness of motion, but it seems as if it's not necessary to get you the conditions of the proof, in some sense, to get you to a stable motion. Stable motion seems to be coupled to the following statement, that if for large phase space quantities, in particular large x and y in this case, the full potential converges to a decoupled potential, where you can look at just a potential for the x mode and just a potential of the y mode, such that that decoupled potential corresponds to, or the decoupled potentials in themselves correspond to stable individual theories. And if that convergence happens fast enough, then you're decoupling the theory at large phase space values fast enough, and therefore you can still achieve stable motion. One way, I think, or another way to think about this is that if you're in the regime where you have fully decoupled the modes, then there is no Ostrogradski instability, right? You can write down two free theories with some individual potentials or interactions. And these will just be decoupled and happily live with each other, or side by side, and not know about each other, and therefore not exchange energy. And if that happens fast enough at high phase space values, then that seems to be sufficient. And in the paper, we spent quite a bit of time of trying to translate this, actually these proof conditions into this statement. And numerics suggest that that indeed is sufficient. So field theory extensions.
Aaron, just wanted to ask just a short question. So
Sure.
although these trajectories, they look like they are pretty bounded in the phase space, but is there like do they develop some chaotic behavior also, or is it there is no chaos that is observed?
There is in some sense local, so there's not really chaos. So there can be points in phase space which are, so what you're saying is related to local stability, I think. So
I see.
there are points in the potential which are locally unstable, and so you have chaos around these points.
Mm-hmm.
But then the theory also has other local points which are Lyapunov stable, so they are locally stable. And around these points, you then have stable motion.
I see.
And
I see.
indeed, that's another interesting aspect, that these models can even also have or induce new locally stable vacua, so Lyapunov stable vacua.
Okay, I see. Okay. Thank you.
All right. Thanks for the question again. As I said, for now, field theory extensions and quantization have not been explored. But I think it's definitely, and both are definitely promising and interesting questions, just because apparently there is this loophole, and it's not clear to me whether that loophole carries over to field theory. Field theory, I think, is more doubtful even than quantization, because if you're quantizing in a stable potential, it seems to me as if the quantized theory should also recover that stability, because quantization is a statement about small scales. All right. Now, so first let me ask, are there more questions about this? All right. So then, yeah?
Yeah, and so this color coding is only time, is it? So
yes, the color coding is only time, that's right.
so lighter colors just correspond to later times or something? Is that?
Yes, precisely.
Okay.
And I mean, I could now go on and track this evolution to even higher times, and you would then fill in the remaining gaps in the phase space volume. You would this butterfly would become all colored. But the point is that it remains in a finite phase space volume, right?
Yes.
Okay. Let me also add that if you change the initial conditions to larger values, you can of course make that phase space volume larger. But that's true also for very normal, without ghosts Hamiltonian system. All right. Then let me shift gears and come back to gravitational actions. And as I said, the model that I'll be looking at is this quadratic gravity here. I'm not particularly married to that, only in the sense that I really think, yeah, Sumati, go ahead.
Yeah, just before you get to gravity, I was wondering if you had looked at just scalar fields, because these are point particle systems, right? So
That's
the
right.
the fact this sort of finiteness of phase-space volume begins to become complicated to even define in the field theory context, even a scalar field. So I was wondering whether you had, in between this and gravity, whether you had looked at scalar fields and scalar field actions.
Yeah, I mean,
Couples.
we haven't wrapped up this work, but indeed it's an interesting question to look at field theories, and in particular, you can probably characterize simple 1+1 dimensional field theories with very similar potentials, and that's something that we are looking into. And the only statement that we are really sure about right now is that these theories do not exhibit fast instabilities, in a sense of that they typically, when you couple modes with opposite sign kinetic terms, you have so-called catastrophic instabilities, which happen on exponentially fast timescales, and then your evolution just ends in a finite amount of time, and you just cannot properly evolve these systems. That does not happen, or at least in the numerics that we've explored, we don't see that happening. The remaining question is whether, whether you see some drift of frequencies to the high frequency regime. So in some sense, whether there's an approach of these theories to higher and higher energies.
Right.
And we cannot yet exclude that there's some logarithmic growth of that type. And so indeed the question is, you're right about that, it's more subtle in the field theory case, and we would love to have a way of making rigorous proofs also in field theory. But integrable field theories are rare and much harder to deal with than point particle systems.
But it's more difficult than it can't be more difficult than gravity. That's, I guess.
No, for sure not. And in gravity, and you will see that in the last part of my talk, it's also a relevant question of whether you have these catastrophic instabilities. And so in that sense, that question is absolutely relevant for gravity, and I have to deal with that in the very same way. The question of physical local stability, or in some sense local for reasonable initial conditions, is something which is, to my understanding, connected to things like cosmic censorship. So it's really a classical gravity question as well, and it's a tricky question in itself, and gravity might have, because of horizons, even superior ways of dealing with that in contrast to these simple field theories which cannot form horizons.
Thank you. Thanks. Sorry.
All right. All right, then let me talk a little bit about this action. Yeah.
Yeah,
Sure.
I have a clarification question. If you can please go back to the previous slide.
Yes.
So here you argued that if for large x and y we can decouple the two motion, then it will the trajectory will become contained inside a finite phase space volume, right? Something like that.
Yeah, that's the basic understanding.
That's the argument. So, but if, for example, for this potential which you denoted here, VL V4.
Yes.
So if you consider large x and y, it is not really decoupled. For example, there will be terms like x square, y square.
That's right. That's right. Exactly. So, that's why yeah.
So are you willing to say that, okay, so there exists some generalized coordinate in which it can be decoupled? It may not be x and y. For example, some eigen directions or something. For example, x plus y by √2 or x minus y by √2, something redefined coordinate in which it may be decoupled. Is that the argument, or? in all coordinate it has to be decoupled.
So this is you're exactly getting to a particular point of this model. You're right that if you are on the trajectory where x and y are equal, then there's a slight subtlety, and that's why I always was careful to say that the full potential converges sufficiently fast to a stable decoupled potential, and the sufficiently fast in these particular models, we understand that it's connected to the Hessian of both the free theory that it converges to, and the interacting full theory. And I think you can understand that because the equations of motion of the two modes are second order in P, so they are second order equations of motion, and therefore the Hessian is sufficient. If the Hessian converges to the free theory, that's sufficient to bound the growth of momenta.
Okay, thanks.
Sumati, yeah? All right, maybe these are remaining hands. I'll proceed. Okay, so in some sense, all of this to me is a toy model because I want to understand actions of this type. And these, just to let you give another, let me go through another iteration of why I think these are interesting. They are interesting as the marginally relevant terms in an effective action. And now it depends on whether you interpret these degrees of freedom as actual physical degrees of freedom or not. If you view this theory as a fundamental theory, then you take these degrees of freedom seriously, and then they actually help you with perturbative renormalizability. So Stelle has then shown that this theory is perturbatively renormalizable. So in some sense, it has a better high energy behavior than general relativity does. It can become asymptotically free, but it definitely exhibits ghosts, such as the one that we looked at in the point particle case before. If you view it as the leading corrections in some gravitational effective action, but you don't take these modes seriously, then you might want to perform field redefinitions, but I think that doesn't change the fact that you have in the particular truncation, you have these additional modes here. And then you would propagate these modes, but not take them as physically serious. So you might want to somehow consider their onset as an unphysical effect. It's not totally clear to me how you would do that in a nonlinear evolution, but that's something that if you want to do that, you have to somehow deal with that. All right, so let me first look at the linear dynamics of this theory. So linear dynamics needs to be performed around some background solution. And here I'm showing you in spherical symmetry the two known asymptotically flat and horizon black hole solutions of this theory. So the one you're familiar with, which is just this line here. So I'm plotting the horizon radius over the asymptotic mass in appropriate units such that the plot rescales with variations in M2. By the way, the scalar mode, this M0 mode, you can forget about that for basically all of my talk because it's not a ghost and it's not exciting, particularly interesting dynamics. So this is just the Schwarzschild solution, right? It's just our horizon equals 2m. And the color I'll explain in a bit. This solution here is a different black hole solution. And it has the interesting property that as you grow in horizon size, you decrease the asymptotic mass. And in some sense, I think that can be viewed as a feature of the fact that you have an opposite sign kinetic mode. You grow the horizon, You decrease the asymptotic mass. So of course, now the first question that you can ask is, are these two solutions linearly stable? And in general relativity, we know that this solution here is, the Schwarzschild solution is linearly stable. In this theory, that's not true. So we also know that there's a branch, which is this one here, which below a certain point, so if the black hole becomes small enough such that it can excite the additional mode, then the Schwarzschild solution becomes unstable to a so-called Gregory-Laflamme instability. And I'll come back to this in more detail. Sumati, yeah?
Yeah, sorry, just too many questions, but
No, that's good.
yeah. Gregory-Laflamme instability, from what I can remember, comes about when you have an extra dimension, a Kaluza-Klein dimension. But here you mean it more generally. I have not seen it in such a. You're still in 4 dimensions, right? I mean, you're not.
That's right. That's right. I'll be very specific about that. And maybe I shouldn't call it Gregory-Laflamme. I should call it linearly equivalent to Gregory-Laflamme.
I see. Okay, you mean to say the equations look similar or something like that?
Not similar, exactly equivalent.
Okay, fine. All right, great. Okay, but the context there, you think of it as the extra dimension being basically.
Exactly. Yes.
Yeah,
Exactly.
and pinching off and so on. So, right. Okay, great. Thank you.
And we find a similar long wavelength instability in the other branch of solutions. And so in that sense, all of the small black holes, so by small I mean horizon size, not mass, all of the small black holes in the theory seem to become unstable due to classical fluctuations. That's just the wrap up of those results. So now let me get into a bit of detail, and then I think I can also answer this Gregory-Laflamme question in more detail. So the question of linear stability is a question of 3 things. It's a question of the linear modes in your theory, the linear dynamics in your theory, your background, and I've shown you the 2 background solutions already, and the boundary conditions that you impose. So let me go through all of those. First, the degrees of freedom. I keep writing down only the action, but in terms of propagating modes, and that's now really what I mean with the statement on the first slides, that this theory propagates a massless graviton. You can decompose the spectrum of the linear equations of motion into a massless spin 2 mode, which you're used to, a massive spin 0 mode phi, and a massive another spin 2 mode, which is massive, which I'll call psi b here. So these are the propagating linear modes. And then you can go on a particular background and you can expand the perturbations on that background, so these ones, into spherical harmonics. So you'll need 2 sets of the spin 2 spherical harmonics and 1 set of the massive one. And then you would expand all of them into these sets. I'll make a simplification here. Just because I know that I'm interested in long wavelength solutions, I can focus on axisymmetric perturbations, which means I'll set the index m of these harmonics to 0, and I'll focus on the monopole, so the lowest lying mode, which is the L equals 0 mode. And then I'm asking, is this particular mode unstable? So this is far from a full linear stability proof. If that mode is stable, you can view it in the other way around. If I find an unstable mode, for sure, the theory has an unstable mode. I can't guarantee that it doesn't have an unstable mode if this particular mode is not unstable. And then you need to go through a lot of algebra, as you see here, that there's all these different functions. You will see that there's only one function which is an actual mode, so that there's only one actual monopole mode. All the other ones are then implied, and so you get to one perturbation equation of this particular form here. People call it a master equation. This r star is the radius, the tortoise coordinate, so the radius stretched down to the horizon, so that you can recast it even to a finite interval and impose boundary conditions on the horizon and on the at asymptotic infinity. So at the horizon, we want to have purely ingoing waves. That's just because we know that the horizon has the property that it's a one-way membrane and nothing comes out of the horizon. So we only have purely ingoing waves at the horizon. But at asymptotic infinity, we have a choice. And outgoing waves correspond to what you might be familiar with, the quasi-normal mode problem. So, right, so assume you have a black hole and you perturb it a tiny bit, or you're in the late stages of a merger and the black hole just rings down to its final state. Then the final modes can be described in terms of a quasi-normal mode spectrum, which means you have outgoing waves at asymptotic infinity, and you might want to record them in some observational experiment. The opposite is ingoing waves at asymptotic infinity, which really is a scattering problem in some sense of whether the wave gets amplified or not as you scatter it off the black hole. And this boundary condition at asymptotic infinity is what tells you about stability. So I'm picking ingoing boundary conditions at asymptotic infinity, and then a positive imaginary part of this frequency omega here, of course, signals an instability, right? If I put a positive imaginary part, that's a growing exponential, and a negative imaginary part signals a stable mode. All right, so results here were known on a Schwarzschild background, and we generalized this equation to arbitrary backgrounds, and therefore can apply it also to this other branch here, at least numerically, because the branch itself is only known numerically. All right, now let me get to the Gregory-Laflamme question again. For the Gregory-Laflamme, or why I call this Gregory-Laflamme, is that this particular potential here takes the exact form than the perturbation equation that excites the Gregory-Laflamme instability in the high-dimensional black string case. And I think the way that you can understand it is that the linearized dynamics of both problems is exactly the same. So in both cases, there's a massive spin-2 mode, which excites that linear instability. The nonlinear evolution, I think, then can and will presumably be very different. There's another raised hand. Is there another question? All right. If there is, please just interrupt me.
Okay.
Yeah.
Can I ask a question?
Go ahead. Yeah.
Next page.
This previous page.
Yeah, this page. I have a question about the definition of bound state.
Yes.
Yeah. In my opinion about the bound state, we often use exponentially decaying wave to define the bound state.
Okay, so here my definition of bound state is really just in terms of which boundary conditions I pick, but it might be related because what one finds is, oh, you mean I only call it a bound state if I find that a stable exponent, so that I find exponential decay. Is that right? Is that what you're asking?
Okay, okay. You mean you define this bound state from the from function or e to minus I omega t.
Yeah, I wouldn't say I define it by this exponential function here. I would say I define it by setting boundary conditions at both the horizon and at asymptotic infinity. And then I can, thereby I define the bound state problem. And then I can ask this equation, given these boundary conditions, does it have solutions for which frequency solutions does it have? And then you will find a tower of solutions in omega. And here I'm interested only in the very first one. And that tower of solutions, if the omegas are stable, is the tower of bound states in that problem. That's my
Okay.
understanding of it.
Okay, thank you.
All right. So now let me just give you the results. And so I hope this, Sumati, clarifies why I call this Gregory-Laflamme. And then let me just show you the instability again. And this really is exactly the same plot that people show you if they talk about the Gregory-Laflamme instability. There's a particular scale which is set by m2 and the radius of the black hole, and some numerical value which is 0.8 something. And below that, the imaginary part of that monopole mode becomes positive, and therefore you have exactly this unstable mode present in the theory, and you start to excite local instability. And in the Gregory-Laflamme case, this instability has been tracked through the nonlinear evolution. Here, for the quadratic theory, this has not yet been done. So in the other side, this mode is stable, and the black hole, at least to all that we know, looks perfectly stable. That's in this green branch here. And on the other side, you have exactly the same situation. You also have a long wavelength instability. Again, this is the particular point. It's the same value for the horizon size. There's a branch point. And above that branch point, you do not find an instability. Here there are different ways of obtaining that instability because the background itself is only given numerically. So there's two ways, either by performing numerics on numerics or by expanding the background in continuous fractions and then performing numerics on that. And here you again find an unstable onset of a mode. And we don't know yet whether that bends down as in the Gregory-Laflamme case and goes back down to 0. Presumably yes, but we haven't followed the numerics that far. All right, so in any case, that explains sort of the picture here on the left, that large black holes seem to be stable, while small black holes are in both branches unstable. All right, let me also highlight that black hole uniqueness in this theory is broken. So there's two branches of black holes, so it's non-trivial in which branch you are. And the effective field theory that you've seen before really just expands about the solution of the previous order, so just about the Schwarzschild branch. Here you would have to set up some other effective field theory, I think. All right, again, are there questions on this part of linear dynamics?
Aaron, I'm sorry, I think you mentioned this, but what was the difference in the two colors again?
So the green is the stable part, or where we do not find an instability. And the red is where we find a linear instability in the spectrum.
Oh. Okay, thank you.
Okay, so with this linear understanding, let me go to nonlinear dynamics. And there I will talk about the modes again in terms of initial conditions. And I will be in particular interested in whether I can even set up a full nonlinear evolution as a partial differential equation. All of that in the end will be important to talk about this part of a gravitational wave signal, which is called the merger, where really the full, where the two black holes merge into each other, and the full nonlinear dynamics of the theory is important. If we want to model this correctly, and if we want to understand whether a signal in this theory looks anywhere close to the signal that we've observed, or to a signal of GR, then we need to understand the nonlinear dynamics. All right, so this has another technical importance in terms of another form of stability, which is called well-posedness of the initial value problem. And just to give you a very simple picture of that mathematical statement, an initial value problem is well posed if three conditions hold. If you set you set initial data on some slice in this case 3+1 gravitational time evolution, and then you evolve along a time direction. And what you want is now that this time evolution persists and exists for all future time. It's unique, so it doesn't branch into different problems. And it depends continuously on small changes in the initial data. So if I put a small bump in the initial data here, this continuously deforms into a bump in the late time data. So for general relativity, Yvonne Choquet-Broha, who amazingly turned 100, and she showed that more than 70 years ago now. And it's a very nice work. So she showed mathematically that such an initial value problem exists for general relativity. And I'll give you a little bit of flavor of the proof in a second. And then there have been lots of people working to put this on a computer to actually simulate a gravitational wave like the one that I showed on the previous slide. And we are trying to do the same for quadratic gravity, simply because there also exists such a formal proof in exactly the same way as Yvonne Choquet-Broha proved for general relativity. David Noakes also proved the same statement for quadratic gravity. And I'll go over that proof. And then now we've performed simulations both in spherical symmetry and now also in 3+1 dimensions to both show that the proof is sound and also to show that it's actually feasible to perform these simulations. All right, so this is now the nonlinear theory, and I'm only showing the principal part of that theory, so only the highest derivative terms. Here you have the massless spin-2 mode, which is just, again, the metric. This really is the same equation that you would be used to in GR. The Ricci tensor and its definition in terms of a traceless Ricci tensor and a trace, so the Ricci scalar. And you could define this on the right-hand side as being generated by some matter terms, which you may call TAB. Here I'm doing something slightly different. I'm still considering vacuum, but I'm now I'm advancing these variables, these curly variables. I'm interpreting them as fiducial variables, which again have their own equations of motion. And that's how you reduce the fourth order equation that you get from just varying the action to such a second order system. You introduce now propagation equations for these additional modes here. So for the fiducial Ricci scalar and the fiducial traceless Ricci tensor. They have, again, box operators acting on it. So they really have also the form of a wave equation here, which helps you in the following. And then they have some terms on the right-hand side, and in particular also some additional derivative terms and some nonlinearities on the right-hand side. And so that is really the full nonlinear system that one must analyze in this particular theory. But it still corresponds to these modes, and then the initial conditions also correspond to these modes. The important part about this system is that you can cast it into a second order quad and diagonal form. And you can see this form up here already, because of the R equation. So there's no second order derivative here and some mixing up here. Derivatives of these equations, a set of equations, a linear diagonal system. Constraints, and you have to, then you can theorem about well-posedness by Leibniz, which states that this well-posed for sufficiently smooth and decompose the system further into we decompose with a spatial metric gamma AB function n and all these additional similar quantities into space. Really spot the initial just as you do in GR. I'm not putting this here because it's that you can spot the spin 0 to this equation, and you can spot the spin 2 degrees of freedom as the lossless sorry, for this answers here. Again, I don't think it's particularly illuminating, but you can count, you really get the same number. Put this on a computer, and that's where I have to thank very largely of performing the numerics, a code that he's been, which is called dendro-GR, which uses technical numerical relativity, adaptive measure, particular PDE scheme, and to see these.
The connectivity is a bit of an issue. Can you just repeat the last couple of things again?
Oh, probably it was just because of the video. I was just thanking Hyun Lim because he's the one who has developed the evolution code that we're using here. So we're now really putting this system of equations onto a computer and actually evolve it in time. And so now we're interested first in numerical stability because of this question of well-posedness. If the theory was ill-posed, you expected that if you change the resolution of your simulation, your evolution becomes shorter and shorter. In particular, if you increase the resolution, you can't evolve the theory further in time. And here we don't see any such problems. So we can add different levels. Here you see different levels of noise, different levels of resolution. And you have the Hamiltonian of your theory as a marker, right? We want the Hamiltonian to be conserved. And we see that after some initial phase, the Hamiltonian just remains conserved up to exactly the level of noise. That's what people call a noise stability test. And so that seems to go well. Here we are evolving a single Schwarzschild black hole with a perturbation of this noise. And in some sense, you can understand this as the computational realization of the linear problem that we had before, that all the different noise here should excite in some combination of all the different modes, and if there's a growing one, you should see it in this spectrum. There's some further stability tests that we perform, but the upshot is that the numerical evolution looks numerically stable. That doesn't mean that it's physically stable. Physical stability is a second question. And physical stability we can look at around the vacuum solutions, so around the Schwarzschild branch of this theory. So indeed, we recover this linear instability that I talked about, right? Remember this instability, which is equivalent to the Gregory-Laflamme instability, and it kicks in below this particular Val combination of M2 and the Planck scale, or M2 and the horizon radius. And then it has some time scale, which you can also infer analytically. And finding that time scale again was our first task. So we now look at the Ricci scalar, which you can view as a proxy of how this instability develops over time. Again, the initial condition is a Schwarzschild or a Kerr black hole, and you add perturbations, and you see how these perturbations grow in time or not. And here you see different curves with different values of m2 over m Planck, and the mass of the black hole is fixed, such that you basically different colors here mean different parts of this regime. So if you're on the red curve, you're on 0.2, so you're really somewhere very close to the peak of that instability. And then on both sides of the instability, you're going down on either direction of the peak. And if you're above actually, I think there's a factor of 4 pi or something like that. So these cases here, which have m2 0.5, they are already in the regime which is stable. Here, this is a case which is very close to 0, and in between you approach the peak of that curve. And so you see that effectively on both sides here and here, you can't see the instability, but this is just because here the growth rate is very tiny. So really stable, I think it's only on one side of the curve. And then an interesting thing is also that there are, let me just quickly finish, that there are no further modes that seem to be more unstable, and this rate seems to match the rate that you would expect here. All right, yeah.
So, so I wanted to just ask, like, this number that you have 0.87, like, is it some kind of you got it? And it's possible to understand it like from something, or you did obtained it like some numerical thing, and you observed that this number is emerging over there.
So here and in my work, we obtain it numerically as really just this number where this behavior changes.
I see.
But there's a nice math paper in which the Gregory-Laflamme instability, because it's the same perturbation equation, is studied. And where there's, I think there's just a proof of instability up to that scale. But there, this number also is derived in some sense in an analytical way.
Okay. Thank you.
All right. So what I want to say is that otherwise, apart from this Gregory-Laflamme instability, it looks like we find a physically stable subsector. And that's, I think, also the stage at which you can interpret our results. You can take the vacuum solution, and you can even now perform nonlinear things on the vacuum sector of that theory. For instance, you can add really physical wave perturbations, so-called Tucholsky waves, which are really just an instance of a gravitational wave around the black hole. They remain stable as far as we see. We can even take a full binary merger. So this is really a simulation of a binary merger with similar initial conditions than the first gravitational wave observation that we had inferred from the first gravitational wave observation. And you see here superimposed the GR evolution, which is the which people have been able to do for a long time, which is the thick light blue curve here, and on top the dashed one is the evolution in our in the quadratic gravity theory. And you really see no difference here, and that holds up to numerical precision. So that really just means that in the full evolution, even if the theory becomes fully nonlinear, it seems that there are no additional instabilities which are excited. And that's really interesting, I find, because it seems that this theory with additional modes can still mimic the vacuum sector of GR. Of course, the interesting question is now, what if we go beyond vacuum? So that already takes me to a little bit of an outlook. We would like to explore the nonlinear endpoint of that instability. We would like to include matter and then work on both gravitational collapse. There's actually been very nice recent work by Ramiro Cayuso on that. We would like to work on finding initial data when including matter, so in particular finding initial data for neutron stars. And then if we have neutron stars in that theory, we can ask the question of how stable or not even systems with matter are. And I think this is where the theory will show different behavior from general relativity, and where you can potentially then exclude parameter ranges of that theory. There's also a comparison question with other approaches on how to do the evolution with higher derivatives. But I think I've already gone over time probably. So I'll just end on this slide where I summarize everything and let you ask your remaining questions. Thanks.
Thanks, Aaron, for the wonderful talk. So now we can have a few more questions from the audience. So, so I wanted to ask one thing. So, in the between, you also mentioned about the uniqueness that is getting affected because of some of the presence of some higher derivative terms, and
you mean uniqueness in the initial value problem, or black hole uniqueness?
black hole uniqueness that you was mentioning in the one of the slides.
Yes.
So like, so this is like for the same initial conditions, like you have two possible solutions, or
No, that's exactly why I asked the question. So uniqueness in the time evolution is something different than uniqueness of the different background solutions, right? So black hole uniqueness in GR has, of course, lots of layers to it. One is simply that if you ask for stationary solutions, the only solution you get in vacuum GR is Kerr.
yeah.
And that's no longer true in that theory. So if you ask for stationary solutions, or in that case, even static solutions, you get more than just the Schwarzschild solution. You get a different branch of solutions. And that opens up the possibility that one of the branches is unstable in a certain regime, and then the theory dynamically takes you to the other branch, and the opposite way around potentially. Of course, it's also possible that both branches are unstable and the theory just decays as you might expect it from considerations of Ostrogradski.
I see. Okay.
All right. Sumati?
Yeah, so a few questions. Thanks for a very interesting talk. I wanted to, so typically when we talk about, so let me start with the first one, which is just to do with the classical solutions that you're looking at. The fact that you have certain black holes, which are, certain solutions, which are stable against perturbations and so on, that linearized stability. It's still, you said there is a theorem that tells you the quadratic gravity has a well-posed initial value formulation for any initial, and I'm supposing that just like in the case of proper GR, it's true for any initial value. But here you're looking at a particular class of solutions and then looking at perturbations. So why is that theorem, the second line on this slide, not going to guarantee the third line? I'm a bit confused about that.
Yeah, I think I should have been more careful in stating that what the theorem tells you is that the initial value formulation remains locally well posed.
I see.
That for some time at least, you're able to evolve it in a well-posed manner. Whether there's a global breakdown of the initial value problem, even in GR, we don't fully know that. And that, again, I think is related to cosmic censorship. So if you're able to scale to something like a naked singularity or so, then of course your time evolution would also end. So if you really were able to prove for all initial data that you have always an infinitely long time evolution, then you would exclude these possibilities, I think. But yeah,
Right.
you're right. That there's more subtlety to that, even in GR, and for sure in this theory here.
Right. And the other thing is that when you talk about these unbounded Hamiltonians, typically the worry is in the in the quantum field theory, what these ghosts mean and so on. Right. So
That's right.
there is one level, the classical theory and stability within the classical theory, but there's also the fear that the quantum field theory is itself not well defined, and you run into all kinds of problems. So classical evolution, especially when you're coming to high derivative things, which you don't imagine to be classical. I mean, strictly not classical. They come in the quantum regime that you have these predictions and so on.
Yes.
As sort of expectation values of things. And so I'm just wondering, how do classical stability of these high derivatives, how can they tell you things about the stability of, or, the well-posedness of the quantum problem? I mean, these are, of course, very general questions, and I just sort of to put it, yeah.
Yeah, no, I think that's a very important question. And I mean, the very short answer is just, unfortunately, I don't know. But I think that it is at least promising if you have a Hamiltonian which is really globally stable, because then, I mean, I think of quantum fluctuations as just a new means of exploring all possible classical solutions, exciting all possible classical solutions. And so if you have a Hamiltonian like this, which really is globally stable, I think it's very, at least intuitively, I would expect that quantizing that Hamiltonian should somehow be possible. It's still, for instance, an interesting question: what's the vacuum, the true vacuum of that Hamiltonian? And then you're absolutely right that if I go to field theory, it's just a new problem. Because there's now infinitely many modes which are coupled, and I can excite higher and higher frequencies. All these notions are in some sense new and worsen the problem if there is an Ostrogradski instability, or if there is truly a runaway. And we don't know yet whether the results on point particles that we have are able to help you with these, or generalize to field theory.
I mean, just related to that is also, I mean, in the quantum theory, you'd want so bounded Hamiltonian, or bounded operators and so on. The absence of boundedness, you kind of do things like consider while operators and so on. So I'm not, but somehow ghosts seem like things that you can't, I mean, so maybe there's a myth there, but there's sort of the sense that anytime you have ghosts in your theory, then the quantum field is just not. So it would be interesting to know, even in the case of, I guess, this is just a general comment, that even in the case of the scalar field, if one could say something, those are very general statements, and I'm wondering whether there's something specific depending on the nature of the classical behavior and how it impinges on the quantum, whether those statements can be defined. Thanks. Just a general comment on it. Thank you.
Just to add one more thing to that, in the quantization, what you would want is that where you're using ladder operators, right? And then you have a choice of which of these ladder operators annihilate the vacuum, and depending on that, in the usual ghost picture, depending on that choice, you either get negative norm states, or you get again this instability problem. And I think there you have a choice, and if you don't have the instability in the classical theory, you might be able to make new choices there. Okay. Or different, yeah, exactly. That's what I think. Okay, thanks.
So any more questions from the audience? Mhm. So one more thing I wanted to ask, like, is it possible to, like, if we suppose we have a like a Lagrangian or a Hamiltonian, like where it is, one can see that in some ways that there is a possibility of appearance of a ghost, and the ghost will exist, and some instability might occur. But is it possible to see that even though the chance of instability happening is there, but this kind of self-containedness will be also existing, and the solutions will not go out of the bounded region. So, is it possible to see something like say something like that by looking at the Lagrangian or Hamiltonian, or there is some condition just based on, like, if I check that thing is satisfied for certain kind of Hamiltonian or Lagrangian, then I can be sure that okay, the solutions will be always will always be contained within a certain region and won't basically just go out of that. I mean, even there might be instabilities, but overall, basically, they will be within bounded, basically.
Yeah, we would really like to have that, and that's also why I tried to understand, or why we try to understand the proof conditions in terms of physical conditions, because I think the physical conditions will be the ones which are generically, which might be generically true, and I think there's still loopholes to those conditions, so I don't think it's clear that you can apply them generically. And of course, they only hold, for now, they only hold for point particle systems. And they are at the level of the Hamiltonians, so you would have to translate them to the respective higher derivative Lagrangian, from which you get the Ostrogradski, by Ostrogradski method, that Hamiltonian. So there's still a lot of steps, I think, that would have to be looked at to understand such more generic conditions. For now, I think we're at the stage of where there's somehow a counterexample to a specific point in the logic following the Ostrogradski theorem. But yeah, that's, I think, what we should aim for, understanding this more generally. I agree.
I see. So, any more questions from the audience? So, let me see if there are any raised hands. No further raised hands. So, then if not, then maybe well, thank you to Aaron and for coming and giving a wonderful online presentation. And this we have recorded, and we will soon upload it in our YouTube channel and the playlist. And hope we will. Oh, Sumati is saying thank you, clapping. Oh, the symbol.
Yeah, thank you also for all the questions. I think it's much more fun for me as well if there's questions.
No, thanks a lot, Aaron. Nice to see you in Bangalore again.
Well, sadly, not really.
In Bangalore.
Oh, well, thank you.
Yeah. So hope to see Aaron again sometime in future. If we plan to organize some conference, then please do come over. And
Aaron, yeah, in fact, I should advertise our online conference next week. It's on our website. I'll send you the link, but hopefully you're coming as well, Gaurav. So it's in honor of Shokib, on Shokib Buha, precisely about the initial value formulation and so on. We've got a very nice list of speakers. So I'll send you the link, and so do register. We have already 190 people who've registered, so we're like, oh my God, we're gonna have a difficult time managing questions, but.
Well, she's one of the most amazing mathematical physicists out there, right? So.
Yeah, absolutely. Anyway, thanks a lot. Thank you.
Thank you
thanks,
as well.
Aaron.
Thanks, Gaurav.
So I'll stop the recording now.
Bye-bye.
Bye-bye.